Have you ever wondered if there's another universe beyond our own? Prepare to have your mind blown, because the James Webb Telescope has just made a discovery that challenges everything we thought we knew about the cosmos. Welcome to our channel. In today's video, we're diving into the latest, groundbreaking discoveries from the James Webb Space Telescope. From the possibility of a universe merging with our own to ancient galaxies that defy current theories. These findings are reshaping our understanding of the universe. Stay tuned as we explore this cosmic revelation. The James Webb Space Telescope has recently focused its powerful lenses on the deepest parts of the early universe. The data it gathered suggests that our universe might have merged with another in its early stages. Scientists have identified strange, ancient galaxies that challenge our current theories, indicating that the early universe may be fundamentally different from the one we know today. We were designed to see the first galaxies that emerged in the universe. And within just 12 hours of observation, the results were beyond our wildest dreams. The James Webb Telescope has unveiled images from over 13 billion years ago, showing a universe that's not what we expected at all. The telescope's recent observations reveal peculiar phenomena that have left astronomers around the globe in awe. Our universe, which began about 13.8 billion years ago, was thought to have a definite beginning, expanding ever since. But new data from the James Webb Space Telescope suggests that our understanding might need a serious revision. At the 2024 International Space Science Institute workshop in Bern, Switzerland, scientists presented findings that challenge the standard cosmic model. They have been meticulously studying the first billion years after the Big Bang, a period when galaxies were in their infancy. Stars were forming, and black holes were becoming more massive. The Hubble Space Telescope could observe up to a redshift of 11. But the James Webb Telescope has pushed that limit to 14.32, observing galaxies just 350 million years after the Big Bang. This includes the detection of carbon in a galaxy only 350 million years old, suggesting that the conditions for life may have been present almost from the dawn of time. These observations are revealing galaxies that don't match theoretical models and computer simulations of the early universe. Scientists now believe that the James Webb Telescope will soon observe galaxies from when the universe was very young, at a redshift of 20. Looking back to when the universe was just a few hundred million years old. Traditionally, it was believed that beyond a certain point, known as the Dark Age, the universe was filled with neutral hydrogen gas, making it opaque and dark. Surprisingly, the James Webb Telescope has discovered galaxies that existed even before this period, challenging our understanding of how and when galaxies formed. These findings raise the profound question of whether we could be looking at an entirely different universe. If our physics is correct, we should see small, young galaxies as we look deeper into the early universe. However, we keep finding massive, mature galaxies. One theory suggests that our universe might have collided with another universe when it expanded rapidly in the early stages, explaining why the laws of physics might vary in different parts of the cosmos. Recent research indicates that the fundamental laws of physics might have been different in the early universe. Gravity, for example, may have been about 1% weaker on very large scales. This small adjustment to Einstein's theory brings our models closer to observed data. Another significant challenge that has emerged from recent observations is the non-uniform expansion rate of the universe. For decades, astronomers have worked under the assumption that the universe's expansion is homogeneous, governed by a single rate that can be measured and quantified precisely. This expansion is primarily attributed to dark energy, a mysterious force that counteracts gravity and accelerates the universe's growth. The cosmological constant, introduced by Einstein, is the term used to describe this dark energy in the equations of general relativity. It has been assumed to be a constant value throughout the universe, uniformly influencing the rate of expansion. However, recent measurements and observations suggest a more complex reality. The idea that the universe is expanding has been a cornerstone of cosmology since Edwin Hubble first discovered in the 1920s that galaxies are moving away from us, with more distant galaxies receding faster than those closer to us. This discovery led to the formulation of Hubble's law, which states that the rate at which a galaxy recedes is directly proportional to its distance from us. The proportionality constant in this law is known as the Hubble constant, h, a crucial parameter in cosmology. Traditionally, the Hubble constant has been measured using two primary methods: observing Cepheid variable stars and supernovae in distant galaxies, and analyzing the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. The first method involves using standard candles, objects with known luminosity, to measure distances and thus the expansion rate. The second method involves examining the temperature fluctuations in the CMB, which provides a snapshot of the early universe. For many years, these methods provided consistent values for the Hubble constant. However, as measurement techniques have become more precise, discrepancies have emerged. Observations of Cepheid variables and supernovae suggest a higher value for the Hubble constant than measurements based on the CMB. This discrepancy has led to what is known as the Hubble tension, a growing problem in cosmology. The Hubble tension suggests that there might be fundamental aspects of the universe's expansion that we do not yet understand. One possibility is that the discrepancy arises from systematic errors in one or both sets of measurements. However, extensive efforts to identify and correct such errors have not resolved the tension. This has led some scientists to propose more radical solutions. One such solution is the idea that the cosmological constant is not actually constant but varies across different regions of the universe. If dark energy is not uniformly distributed, this could lead to variations in the rate of expansion in different parts of the universe. This would mean that the universe is not expanding at a uniform rate, but rather at different rates in different regions. This idea is supported by some observations that indicate variations in the distribution of galaxies and large-scale structures in the universe. For example, some surveys of galaxy clusters suggest that there are anisotropies, irregularities in the distribution of matter, that could be explained by variations in dark energy. If dark energy is indeed variable, this could have profound implications for our understanding of cosmology and the fate of the universe. Another possible explanation for the non-uniform expansion rate is the existence of new, undiscovered physics. Some theories propose that the discrepancy in the Hubble constant could be due to modifications in our understanding of gravity. For example, theories that extend or modify general relativity could potentially explain the observed differences in the expansion rate. These theories suggest that gravity might behave differently on cosmological scales than it does in the more familiar environment of our solar system. Additionally, there is the intriguing possibility that we are observing effects of a multiverse, where different regions of space-time have different physical properties. In such a scenario, our universe might be one of many, each with its own distinct laws of physics and expansion rates. This could explain why measurements of the Hubble constant vary depending on the method and the region of the universe being observed. The James Webb Space Telescope is opening our eyes to mysteries we never imagined. Its discoveries suggest that our current understanding of the universe is incomplete and that there might be a lot more to uncover. Are we missing something fundamental, or is the early universe truly beyond our grasp? Let us know your thoughts on these exciting discoveries in the comments below. Don't forget to like, subscribe, and share this video with fellow space enthusiasts. Thanks for watching, and until next time, keep exploring the cosmos.